Yes, it is generally allowed to connect multiple three-phase electrical motors from a main switch cabinet to a secondary junction box using a multi-conductor cable. UL 508, a standard for industrial control equipment, allows the use of multi-conductor cables for connecting motors to control panels. The multi-conductor cable must be rated for the voltage, current, and temperature requirements of the motors. The junction box must be rated for the number of conductors and the total current flowing through it. All connections must be properly made and protected against vibration and loosening. Yes, you can use a 16-conductor cable to connect the main panel to junction box, which then connects to 4 individual 4-conductor cables leading to each motor. Yes, you can use a 13-conductor cable where 3 conductors are allocated for each motor, sharing one common grounding lead. However, this configuration may not be suitable for all applications due to potential interference between motors. It is important to consult with a qualified electrician to determine if this configuration is appropriate for your application. The multi-conductor cable should be routed in a way that minimizes exposure to damage or interference. The junction box should be located in an accessible and well-ventilated area. All electrical installations should be inspected and tested by a qualified electrician to ensure compliance with applicable standards and safety regulations. Now let's delve deeper into the specifics. When designing an electrical system involving multiple motors connected via multi-conductor cable, you need to consider several crucial aspects to ensure safety, reliability, and code compliance. These aspects include conductor sizing, overcurrent protection, grounding, voltage drop, and the suitability of the components used. Conductor sizing is paramount. You must select conductors within the multi-conductor cable that are adequately sized to carry the full load current of each motor they serve. This requires calculating the full load amperage, or flow, for each motor using the motor's nameplate data and relevant tables in the National Electrical Code, or NEC. NEC Table 430.24 provides guidance on sizing conductors for multiple motors. The general rule is to calculate 125% of the full load current of the highest rated motor in the group, then add the full load currents of all the other motors in the group. This sum determines the minimum ampacity required for the conductors in a multi-conductor cable feeding the junction box. Remember to factor in ambient temperature and conductor bundling when determining the appropriate conductor size. Higher ambient temperatures and bundled conductors can reduce the ampacity of the conductors, necessitating larger wire sizes. NEC Table 310.15 addresses ampacity correction factors for ambient temperature, and NEC Table 310.16 covers ampacity rating for conductor bundling. Overcurrent protection is another critical consideration. Each motor must have its own individual overcurrent protection device, typically a circuit breaker or fuses, to protect against short circuits and overloads. These overcurrent devices are usually located in the main switch cabinet. The size of the overcurrent protection device must be selected according to NEC Article 430. This article provides detailed rules for selecting the appropriate size of overcurrent protection devices based on the motor's full load current, starting current, and the type of motor. The overcurrent protection devices must be coordinated to prevent nuisance tripping and to ensure that only the faulted motor is disconnected from the power source. The multi-conductor cable itself must also be protected against overcurrent. This is typically achieved by installing a main overcurrent protection device at the point where the cable originates from the main switch cabinet. The size of this overcurrent protection device should be based on the ampacity of the multi-conductor cable, as determined by the conductor sizing calculations. Grounding is essential for safety. All motors and the junction box must be properly grounded to provide a low impedance path for fault currents. This helps to minimize the risk of electric shock and equipment damage in the event of a ground fault. The grounding conductor must be sized according to NEC Table 250.122, which specifies the minimum size of equipment grounding conductors based on the size of the overcurrent protection device protecting the circuit. In the case of a 13-conductor cable with a shared grounding conductor, you must carefully evaluate the adequacy of the grounding conductor size. The shared grounding conductor must be sized to carry the maximum ground fault current that could occur in any of the motor circuits. If the shared grounding conductor is not adequately sized, it could overheat and potentially create a fire hazard. It's generally recommended to provide individual grounding conductors for each motor to ensure adequate grounding protection. Voltage drop is an important factor that can affect motor performance. Excessive voltage drop can cause motors to overheat, reduce their torque, and shorten their lifespan. The voltage drop in the multi-conductor cable should be calculated to ensure that it does not exceed the limit specified in the NEC. The NEC recommends that the voltage drop for power, heating, and lighting circuits should not exceed 3% at the furthest outlet or load. To minimize voltage drop, use larger conductors, shorten the length of the cable, or increase the supply voltage. Component suitability is another crucial aspect. All components used in the electrical system, including the multi-conductor cable, junction box, connectors, and overcurrent protection devices, must be rated for the voltage, current, and environmental conditions in which they will be used. The multi-conductor cable must be suitable for the type of installation, such as wet or dry locations, and must be resistant to abrasion, chemicals, and other factors that could damage the cable. The junction box must be sized to accommodate all of the conductors and connections, and must be rated for the maximum current that will flow through it. The connectors must be properly installed and tightened to ensure a reliable electrical connection. In addition to these technical considerations, you must also comply with all applicable codes and standards. The NEC is the primary electrical code in the United States, and it provides detailed requirements for electrical installations. UL standards also provide valuable guidance on the design and construction of electrical equipment. UL 508A, as previously mentioned, is a specific standard for industrial control panels. It's essential to consult with a qualified electrician or electrical engineer to ensure that your electrical system complies with all applicable codes and standards. They can perform the necessary calculations, select the appropriate components, and inspect the installation to ensure that it is safe and reliable. Now, let's consider the two specific configurations you mentioned. Firstly, using a 16-conductor cable with individual 4-conductor cables for each motor. This configuration provides the greatest degree of flexibility and isolation between the motor circuits. Each motor has its own dedicated set of conductors for power and grounding, minimizing the potential for interference or ground loops. This configuration is generally recommended for applications where motor performance and reliability are critical. Secondly, using a 13-conductor cable with a shared grounding lead. This configuration can be more cost-effective as it requires fewer conductors. However, it also has some potential drawbacks. Sharing a grounding conductor can increase the risk of ground loops and interference between the motor circuits. It can also make it more difficult to troubleshoot ground faults. This configuration may be suitable for applications where the motors are relatively small and do not draw a lot of current, and where interference is not a major concern. However, it's crucial to carefully evaluate the suitability of this configuration for your specific application. Furthermore, consider the impact of harmonic currents. Nonlinear loads such as variable frequency drives, or VFDs, can generate harmonic currents that can flow through the grounding system. These harmonic currents can cause overheating of the grounding conductors and can also interfere with sensitive electronic equipment. If you are using VFDs to control the motors, you should consider using a separate grounding conductor for each motor to minimize the impact of harmonic current. Also, think about the physical installation of the multi-conductor cable and junction box. The cable should be routed in a way that minimizes exposure to damage from mechanical stress, chemicals, or extreme temperatures. The junction box should be located in an accessible location for maintenance and troubleshooting. The junction box should also be properly ventilated to prevent overheating. Use appropriate strain relief methods where the multi-conductor cable enters the junction box to prevent stress on the conductors and connections. Consider using flexible conduit or cable glands to provide strain relief and protect the cable from damage. Label all conductors and terminals in the junction box to facilitate troubleshooting and maintenance. Use wire markers or terminal blocks with clear labeling to identify each conductor and its corresponding motor. This will make it much easier to trace circuits and diagnose problems in the future. When making connections in the junction box, use appropriate connectors and terminals that are rated for the voltage, current, and wire size. Ensure that all connections are tight and secure to prevent overheating and arcing. Use a torque wrench to tighten the connections to the manufacturer's specified torque value. Regularly inspect the electrical system to ensure that it is in good condition. Look for signs of damage such as cracked insulation, loose connections, or corroded terminals. Also, check the temperature of the conductors and connections to ensure that they are not overheating. Perform regular maintenance on the electrical system, such as tightening connections, cleaning terminals, and replacing worn or damaged components. Keep a record of all inspections and maintenance activities to track the condition of the electrical system over time. This will help you to identify potential problems before they become serious. Remember that electrical work can be dangerous. Always to energize the circuit before working on any electrical equipment. Use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and insulated tools. If you are not qualified to perform electrical work, hire a qualified electrician to do the job. Now let's talk about documentation. Maintain thorough documentation of the electrical system, including wiring diagrams, component specifications, and test reports. This documentation will be invaluable for troubleshooting, maintenance, and future modifications to the system. Create a detailed wiring diagram that shows all of the conductors, connections, and components in the electrical system. The wiring diagram should be clear, accurate, and easy to understand. Include the wire size, type, and color code for each conductor. Also, include the manufacturer and model number for each component in the system. Keep a copy of the manufacturer's specifications for all of the components in the electrical system. These specifications will provide important information about the voltage, current, and temperature ratings of the component. They will also provide information about the installation and maintenance requirements for the components. Perform thorough testing of the electrical system after it is installed and after any modifications are made. Testing should include insulation resistance testing, continuity testing, and voltage drop testing. Keep a record of all test results, including the date, time, and test parameters. These test results will provide a baseline for future comparisons and will help you to identify any potential problems with the electrical system. Periodically review and update the documentation as needed to reflect any changes or modifications to the electrical system. This will ensure that the documentation remains accurate and up to date. Consider using a computerized maintenance management system, or CMMS, to manage the documentation and maintenance activities for the electrical system. A CMMS can help you to track the condition of the electrical system over time, schedule maintenance activities, and generate reports on the performance of the system. Remember that proper documentation is essential for ensuring the long-term reliability and safety of the electrical system. It can also help you to comply with regulatory requirements. As technology evolves, so do electrical codes and standards. Stay informed about the latest updates to the NEC, UL standards, and other relevant regulations. Attend industry conferences, read trade publications, and participate in online forums to keep abreast of the latest developments. This will help you to ensure that your electrical system is always in compliance with the latest requirements. Consider joining professional organizations such as the Institute of Electrical and Electronics Engineers, or IEE, or the International Association of Electrical Inspectors, or IE. These organizations provide valuable resources for electrical professionals, including training courses, technical publications, and networking opportunities. They can also help you to stay informed about the latest developments in the electrical industry. Regularly review and update your electrical system to incorporate new technologies and best practices. This will help you to improve the performance, reliability, and safety of the system. For example, you may want to consider upgrading to energy-efficient motors, using smart motor controllers, or implementing predictive maintenance techniques. By staying informed about the latest technologies and best practices, you can ensure that your electrical system remains state-of-the-art. In conclusion, connecting multiple motors to a single multi-conductor cable is a complex task that requires careful planning, design, and execution. By following the guidelines outlined in this discussion, you can ensure that your electrical system is safe, reliable, and compliant with all applicable codes and standards. Remember to always consult with a qualified electrician or electrical engineer for assistance with your electrical projects. They can provide valuable expertise and guidance to ensure that your electrical system meets your specific needs.